Hi, my name is Zhen. Thanks for watching our presentation. Our paper is called Consistent Multimodal Generation via a Unified GAN Framework. The whole project is finished through collaboration between UIUC and Adobe. In the past few years, we have witnessed the rapid progress in generating visually appealing to the images in an unconditional manner. A typical example is the very powerful cell GAN models, and now the diffusion models. Most methods focus on generating RGB images or the transfer from one modality to another. However, only a few works focus on generating mutually consistent modalities. Here, we define modality as one type of image analysis, which can be depth, surface normals, albedo, optical flows, etc. Generating multiple modalities together has tremendous value. For example, in our work, we present that our method can generate dataset to enhance the performance of downstream discriminative tasks. And we can leverage a cross-domain fine-tuning strategy to extend the model to another domain with relatively fewer pairwise data of the target domain. Assuming that we are interested in generating images and depths, the generator has a shared backbone for both modalities. The consideration is different modalities share the same underlying structure, so it is easier to learn a unified structure from the first place. At later layers, since representations for decoding different modalities differ, we build modality-specific branches. This generator architecture can be easily extended to support more modalities. For example, if we add surface normal, we can simply build another branch and add it to the same layer index. Discriminator is critical to GAN training. In our work, we developed two types of discriminators. Firstly, the fidelity discriminator are built separately for each modality and is mainly used to check whether the input modality is real or fake. Secondly, we have a single consistency discriminator that receives the input as the concatenation of all modalities and is used to check whether the input pair is consistent or not. We found that without the consistency discriminator, although the synthesized outputs are realistic, they do not match with each other. Our discriminator architecture is also scalable. For a new modality, we only need to build a new fidelity discriminator since the consistency discriminator is shared across all the modalities. Besides, we also use adaptive discriminator augmentations. One counterintuitive fact here is we apply the same suite of augmentations to all modalities. In discriminative learning approaches, sometimes you should be very careful when doing augmentations on such as surface normals or depths. However, here, even if we do crazy augmentations, the generator still learns. This is a good merit in scalability compared to discriminative approaches. In this work, we only utilize adversarial loss for training. This is also a key difference to discriminative approaches, which build separate loss functions tailored for different tasks. Our loss is simple and easily applicable to more modalities. All of our experiments are conducted on the Stanford 3D dataset. For the evaluation metrics, we utilize FID of each modality to capture its fidelity. To evaluate the consistency between synthetic depths and RGB images, we estimated depths from the generated RGB images using Deep Library 3 and then calculate the squared log scale invariant error between estimated depths and generated depths. Similarly, we can calculate other consistency metrics from other modalities as long as we have the corresponding estimators to give pseudo labels. We compared to two prior works, RGB GAN and depth GAN, by generating depth and RGB simultaneously. As can be seen from these visuals, their generated depths are meaningless since the training diverged. Another type of works build additional networks on top of a frozen RGB style GAN generator. However, they usually require annotations for the other modalities they tested, such as segmentation. To compare with them, we first train an RGB generator. After that, we build a depth branch and then train it using the supervision from an Oracle depth estimator. If we train a depth estimator using the Stanford 2D3D dataset as the Oracle estimator, it is denoted as RGB to depths. If we use the off-the-shelf depth estimator as the Oracle, it is RGB to depth star. As shown in this slide, our results have clear contours and structures in depths, whereas all other methods fail to capture that. Here are more qualitative results in the form of videos. We also experiment with adding surface normal. These qualitative results show that our method supports adding more modalities and generate consistent outputs. We compare estimated modalities with generated modalities. As can be seen, our generated depths and normals have more details in the first two rows. In the last row, the generated depth is more reasonable than the estimated depths. All of these estimated normals are blurry at some surfaces. This also tells that the estimators are not always reliable, and generating multiple modalities together can better alleviate local inconsistencies. Another disadvantage of estimated depths is the inconsistency across frames. From these videos, estimated depths show considerable flickering artifacts, but our generated depths are smooth across all time steps. The consistent generation may offer a benefit to unify a scene from different perspectives. In reality, there are cases that we may have limited amount of pairwise data in a domain, but have decent amount of RGB images. The pairwise data is not enough to train a generator from scratch, but the training can be relatively easier if we perform cross-domain adaptation. To deal with the imbalance between pairwise data and unpaired data, we only let the consistency discriminator see the pairwise data and the fidelity discriminators see all data of the corresponding modalities. However, this might skew the generator towards generating realistic outputs without focusing on consistent generation. Therefore, when sampling the data for training, we equally sample the pairwise data and unpaired data. Here in this experiment, we hold out a scene, which is the auditorium from the Stanford 2D 3D dataset, and use the rest data to pre-train a generator. As a result, we cannot see any scenes related to auditorium from the pre-trained generator. Then we perform cross-model fine-tuning using 5%, 10%, and 15% of pairwise data. When using more pairwise data to fine-tune, we get better performance on the auditorium scene, but our method already has a good performance using 5% pairwise data. Another application is we can generate pairwise synthetic dataset for downstream tasks, especially under the low data region. We evaluate this property of our model in the task of depth estimation. For this experiment, we first train our model using 20% of real data randomly sampled from the whole training set. Then we are able to use our trained generator to synthesize any amounts of training data. Our idea is to train a depth estimator jointly using both the 20% real data and our synthetic data, and then we evaluate the performance on the validation set. We perform several experiments by varying the amount of synthetic data. In the left two plots, we show the results of using both real and synthetic data for training. The dashed horizontal lines are the performance obtained using the corresponding percent of real data. As we can see from the curve, using more synthetic data gives better performance on both metrics, and the performance improvement is more significant when the total amount of data points is relatively small. We observe a similar trend in using synthetic data only on the right two plots. They validate that the synthetic data alone can be regarded as a trustworthy source to train depth estimators. To summarize, we propose a unified GAN framework for consistent multimodal generation. Our method is easily scalable to more modalities and or different domains with limited pairwise data. We show that our method has various applications and can serve as data generator for discriminative tasks, such as depth estimation. Thanks for listening, and these are the QR codes for our paper and code. Please take a look if you're interested.